than sitting here and doing all the math. Okay, so this estimating thing is very important. So if you got a base 10, you can do that. If you got base 2, a lot of you can either divide by 2 in your head, divide by 2 and count how many times, or you can actually do divide by 2 on your calculator. I kid you not, I had a graduate. Guy was just about ready to finish my program, and he really had forgotten how to take logarithms and solve this properly. And there was something on the national exams, and I saw him over there, divide by 2, divide by 2, divide. And it was actually divide by 2 13 times was the correct answer. It was between 13 and 14. And he was very careful, and he did it several times to make sure he got it right, and he did it right, okay? So he had a good practical sense of this. So I just want you to have a good practical sense. We didn't actually do the logarithms and solve it, but just realize what's really going on behind those logarithms and the estimating that you can do. All right? And many times in industry, honestly, we don't have you pulling out the calculator and doing logarithms. We make you do it in this course. We make you understand the process, but many times if we've got something logarithmic to happen, a lot of times we'll hide all this logarithmic process in a graph, okay? And we'll put up data, and you may have to go look up data, and you'll have to go use a logarithmic graph. This is one that you might have to use out there in industry. What happens here is we have this, notice it says beta particle range energy curve. And what we have here is energy in MeVs on the y-axis, our range, which are in the units of milligrams per square centimeter. And don't get wigged out about the units. I'll just tell you that this is a graph that if a beta particle has a certain amount of energy, it can go through material a certain range with these weird units, and then we take the weird units and we make them something practical. But this graph, you can see that this is not a straight line, even when it's on a logarithmic. And notice what happens here on the x-axis here. We have 0.01, and then we have an equal space, and it goes to 1, and then another equal space, 10, 100, 1,000, 10,000. So every equal spacing that we have here is going up by a factor of 10. So it's an LOG, a common base rhythm log graph. When you see this, we know that it's going up by a factor of 10. Same thing on the energy. Notice this major division right here is 0.01. The next major division is 1.0, and the very top is 10. So if you take a look at each one of the smaller divisions, notice here we are right here. Okay, everybody see where I'm at? That says 2. Well, what's 2 mean in that? Well, we got 0.01 here at this line, at this major line here, and we have 1.0. Well, what's a 2 between 0.1 and 1.0? It almost has to be 0.2. So this is 0.2. This is 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9. Notice that also on a logarithmic graph, the linear numbers 2, 3, 4, 5, 6 also get closer and closer together as you get closer to the next unit. And then they spread out. Notice we got 1.0, and then it's 2, 3, 4, and this is 2.0 MeVs, 3, 4.0, 5.0, 6.0, 7.0, and on up. And so we may have to, we can use this graph either way to figure out information we want. So we're going to race here real quick, and let's do some sample problems. Let's say that you happen to know that you were working with phosphorus 32, P32. And phosphorus 32, you look up in the chart of nuclides, and you find out its maximum beta energy is equal to 1.7 MeV. And you would like to know, I want to shield out all the betas and make it so that I put enough shielding that all the betas can be shielded. So that means, there may be some betas that came off with phosphorus 32 that are only 0.4 MeVs, but they're not going to go as far and penetrate as hard as 1.7. There may be some that are 1.5 MeVs, but that won't penetrate as. But we know that 1.7 MeVs is the absolute maximum energy that of all the possibilities that this beta particle could come off. So if we shield for a 1.7 MeV beta, all the other betas that come off of phosphorus-32 will be shielded. Well, what kind of range of material will we need to shield that? Well, that's why this graph is used. And we need to go in at this graph. What you do is you go into the y-axis here on the energy side, and you go to the line and see this line here that's going up through here. That's our line. Experimentally, we've figured out that this much energy turns into this much range. So what we're going to have to do is we're going to have to go across and find out whatever energy, intersect with the line, and then drop straight down, and that'll tell us our answer and our range. Now, I didn't do that in the right place, so I'm going to erase those now, but that's a general idea, is we're going to go in on the energy side and figure out where this 1.7 MeVs intersects with that line. But the first problem is, where is 1.7 on this graph? Oh, well, let's see here. Could it be right here? Well, let's see if that even makes sense. Well, this is 0.01 MeVs here. This is 0.1 MeVs. 1.7 can't fit in between these two, right? No, that can't be it. Well, let's look between the next two. What you do is you look between each one of the big numbers off the side. Well, this is 0.1 and this is 1.0. So 1.7 does not fit in between these two. But this is 1.0 MeV and this is 10 MeV, so guess what? 1.7 must be somewhere in here, somewhere between this bracketed area. So now we just got to figure out where is 1.7. Well, we said if this is 1.0 and this is 10, each one of these must be 1.0, 2.0, 3.0, 4.0, 4. So now we say, well, if this is 1.0 here and this is 2.0 here, 1.7 must come in between there. And so now each one of these smaller lines, here, 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 these horizontal lines, each one of those are 0.1. So if this is 1, this is 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.